today's world, there are dozens of different engines and dozens of different carburetors. At Briggs & Stratton, we know that your business depends on your ability to diagnose engine and carburetor problems quickly and on your ability to correct those problems on the first try. That holds true whether you're working on an older style carburetor or the state of the art. A solid understanding of carburetor theory is your key to those quick and efficient repairs. You see, troubleshooting through guesswork does not work. It's time-consuming, expensive, and frustrating. Successful troubleshooting means that you understand what is supposed to happen, you know how to test for whether it is happening, and you know how to interpret results. And yes, experience plays a big role too. It's our responsibility to provide the knowledge of carburetor theory. That's what this video is designed to do. The experience? Well, you'll need to supply that yourself. Let's begin with a basic review of how all carburetors work. We'll do that by building one from the ground up, just as we did in our previous carburetor theory video, PM5127V. Carburetors begin with a simple tube. One end of the tube has a flange, which lets us attach the tube to the engine. This tube directs air into the intake port. Next, we need a fuel supply, so we add a bowl of fuel below the tube. But how do we get the gasoline from the bowl into the air passing through the tube? We use a little pressure. You see, there's a principle, Bernoulli's principle, which basically says that if you increase velocity of a fluid, in our case air, in a confined area, you see a decrease in pressure. So, we need to decrease the air pressure in the tube by increasing the velocity at which the air is moving through it. We do that by creating a narrowing in the tube, known as a venturi. The air must increase its speed in order to maintain the same volume of air passing through the venturi. The result of this increased airspeed is an area of low pressure within the venturi. This pressure difference between atmospheric pressure and the lower pressure in the venturi can be used to push fuel. We know that if we put some gasoline between the high and low pressure areas, the higher pressure will push the gasoline toward the lower pressure through the tube and into the airstream. We just need a way to get sustained high pressure on the fuel in the bowl in order to maintain fuel delivery. So, we add a bowl vent. It allows air pressure to continually press down on the fuel in the bowl, which in turn pushes the fuel up the tube and into the venturi. At this point, we have a simple working carburation system, which would allow an engine to run at one speed. But in most cases, one speed's not enough. By adding a throttle plate to control the airflow, we can also control the engine's speed at any given load. A fully open throttle plate allows maximum airflow, and that increases the difference in pressure between the surrounding air and the air moving through the venturi. As we close the throttle plate, the airflow and the air pressure difference between the atmosphere and the venturi decrease. As a result, the fuel flow and engine speed decrease. But we need better or more accurate control over the flow of fuel coming through the tube and into the airstream. What you see here is one solution, an adjustable needle, which is common on older style carburetors. In newer carburetors, you're likely to find a fixed jet system, and we'll look more closely at those a little later. Either solution will take care of most of our engine's needs. But what about when an engine needs to run at very slow speed? We could slow the engine by continuing to close the throttle plate, but eventually we'd reach a point where the air pressure difference is too small to continue to push fuel up the tube. When ability to run at slow speed is a concern, an idle system can solve the problem. Here's how it works. While closing the throttle plate lessens the air pressure difference between the venturi and the fuel bowl, it increases pressure differences in some other areas of the carburetor. One place where we can gain a significant pressure difference is between the engine side and the venturi side of the throttle plate. As the throttle plate begins to close, the air moving past it increases in velocity. and that results in decreased pressure at the edge of the throttle plate. We can use this pressure difference to move fuel at slower engine speeds. By creating a passage from the fuel in the bowl to the engine side of the throttle plate, we can use that area of decreased pressure to allow the higher outside atmospheric pressure to push fuel through the idle passage and into the airstream. Now, when the throttle plate is open, fuel is pushed up the high-speed tube. And as the throttle plate begins to close, fuel drops down the high-speed tube and is pushed up the idle fuel passage instead. Again, we want to be able to fine-tune the amount of fuel entering the idle circuit. So, we'll add an adjustment needle here, just as we saw earlier in the high-speed system. Now, we've completed our basic carburetor. If we attached it to an engine, it would do the job. However, we can still make a few improvements. For example, a choke system to make cold starting easier. Another modification, which will allow the engine to run more efficiently, is the addition of an air bleed to the main nozzle or emulsion tube. The air bleed allows a metered amount of air to enter the tube along with the fuel and starts to break up or vaporize the fuel before it even enters the venturi. Since it's the gasoline vapors which actually burn, this improves the engine's performance and also offers low pressure relief under no-load conditions. An air bleed can also be added to the idle system to provide similar benefits, as well as preventing extremely rich running at no-load idle speeds. A final modification involves improving the smooth acceleration of the engine from an idle RPM to a top no-load governed speed. You see, when we switch from the idle to the high-speed circuit, there's a momentary lull in transferring fuel from the bowl to the airstream. One solution is to add some transitional fuel passages to the idle circuit. Now, as the throttle plate opens and the engine accelerates, the low pressure area moves to the transitional holes. These passages add fuel to the airstream and maintain fuel supply to the engine. Now that we have a working carburetor capable of sustaining engine operation for as long as the fuel supply lasts, and a working knowledge of basic carburetor theory, is that enough? In today's world, the answer is no. The past few years have seen a number of enhancements in carburetor design, changes which you must understand in order to successfully troubleshoot and repair newer carburation systems. For example, since the mid-1980s, fixed jet carburetors have become more common in many engine applications. In some carburetors, the idle circuit has been removed. This was done both to provide consistent performance and to comply with new emission control standards to be implemented in the near future. This change affects only engines which are rarely run at idle, such as rotary lawnmower engines. Our customers have dictated some changes as well. Pilot jets and anti-after fire solenoids are examples of components developed specifically to meet customer expectations. And finally, new standards for emissions have resulted in a change from adjustment screws to idle mixture adjustment limiter caps, and in some cases, the removal of all adjustments. Let's take a closer look at some of these changes and the theory behind them. In the carburetor we just finished building, you saw two areas where the air-fuel mixture could be adjusted: at the idle circuit and the high-speed circuit. Many technicians thought these adjustments were replaced by fixed jet systems to prevent tampering by consumers or technicians. That is just not the case. One important reason fixed jet systems were developed was to address a common problem: vapor lock. You see, gasoline actually prefers to be a vapor. When it is in a controlled environment, like a tank, fuel line, or fuel filter, the vapor can't readily escape, so it forms bubbles instead. All fuel systems contain small bubbles of gasoline vapor, and they are especially common in a carburetor's fuel line and circuits. There are three factors which influence the number and size of the bubbles formed: the volatility of the fuel, the temperature of the fuel, and the vibration in the system. Normally, these bubbles pass through the fuel lines and carburetor circuits without incident. If any of the three causes we just mentioned are present, however, the size and number of bubbles can increase. In recent years, it's become more common to use blended fuels, which combine gasoline with alcohol and ethers. The more alcohol or ethers in the blend, the hotter the engine runs. The higher temperature increases bubble production and increases the chance of vapor lock, which can affect engine performance and may stop the engine from running at all. Let's take a closer look at how those bubbles and vapor lock created problems in some adjustable jet carburetors. As the bubbles increased in number and size, occasionally one would lodge itself at the annulus of a jet or needle and seat. That bubble now takes up space, which would normally contain fuel, and in effect leans the mixture in the carburetor. When an engine runs under lean conditions, the temperature of the engine rises, and so does the temperature of the fuel. This, in turn, causes another increase in bubble production, and more bubbles lodge between the needle and the main jet. This creates even leaner conditions, which raises temperatures, which creates more bubbles, and on in a vicious circle. Now our carburetor has become little more than a bubble-building machine. As the bubbles become bigger, the number of bubbles begins to decrease. That's because the size of the bubble is controlled by its internal pressure. And when two bubbles with approximately the same internal pressure touch, they join together. Eventually, we can wind up with a few big bubbles. When the internal pressure in those bubbles becomes equal to or greater than the head pressure of the fuel, all fuel flow stops. And that is vapor lock. Now that we have a better understanding of vapor lock, let's see how a fixed jet system corrects it. In a fixed jet system, there's one relatively large hole for the fuel and the bubbles to pass through. In fact, the area of that single hole is equal to the total fuel flow area for an adjustable style carburetor when it is properly adjusted. Only an extremely large bubble could possibly block that hole and create vapor lock. Now, how does the fixed jet system actually work? An important component is the emulsion tube. This tube has a series of holes and a sealing area. It may also contain a jet or orifice. An important point to understand is that the jet limits the amount of fuel that is allowed to refill the emulsion tube when the engine is running. The fuel level in the emulsion tube varies based on engine load or throttle plate position. To understand how the emulsion tube works, let's look at 4 examples. When the engine is running with no load, the fuel level in the emulsion tube is the same as in the bowl. The fuel is being delivered through the transitional holes. So far, the engine doesn't need any more fuel than can easily flow through the jet near the base of the emulsion tube. Now, let's look at what happens when the engine begins to work under a light load, such as turning a mower deck. As the engine begins to work harder, the fuel level in the tube drops slightly below the fuel level in the bowl. The jet is a limiting device. Only a specific amount of fuel can flow through the orifice in a certain amount of time. When the engine uses more fuel than can be allowed through the jet, the fuel level in the emulsion tube drops. When the engine is running under a moderate load, the level in the tube drops even further. At this point, there's a significant difference between the level in the tube and the level in the bowl. Again, the limiting factor is the amount of fuel that can pass through that orifice in a certain amount of time, compared to the amount of fuel the engine is actually consuming. At this point, the high-speed air bleed feature comes into play. The air bleed acts a lot like a bowl vent. It allows atmospheric pressure to act on the fuel in the emulsion well. With sustained pressure and airflow into the emulsion tube, fuel and air are forced up the tube and into the venturi. As the fuel level decreases, it exposes holes in the emulsion tube to the air entering from the air bleed. This allows more pathways for the air to get into the tube and start mixing, which speeds up the vaporization process and helps the engine run more efficiently. Our 4th example is when the throttle plate is wide open and the engine is doing all the work it can. The engine needs the maximum amount of fuel that can be supplied through the jet. As a result, the fuel level drops until there's essentially no fuel level at all in the emulsion tube. At this point, the fuel flows directly through the jet into the emulsion tube and is delivered to the venturi. Now, let's take a look at another aspect of today's modern carburetors. In systems which still feature an idle circuit, you'll often find a pilot jet, a fixed jet for the fuel introduced into the idle circuit and into the transitional hole reservoir. The pilot jet restricts the fuel coming up from the bowl into the idle circuit as engine conditions change. At idle, the fuel delivery is not restricted very much. That's because a very small amount of fuel is needed to maintain idle speed. However, when the engine moves to top no-load speed or becomes lightly loaded, the pilot jet begins to affect the engine's performance. The size of the pilot jet's orifice provides just the right amount of fuel needed to maintain the proper speed when the engine is lightly loaded. As the fuel and air begin to mix in the pilot jet, the mixture may move into a cavity where transitional holes are drilled. This cavity or reservoir will be covered by a Welch plug. The holes shown here deliver the fuel when the engine is idling or under light load. Some carburetors provide a mixing area within the pilot jet itself. Different pilot jets are used in various carburetors, depending on the application. Now, let's look at one more relatively new component of modern carburetors. We've all heard the awful sound of after fire that sometimes occurs a few seconds after an engine is turned off. Even though the ignition's off, most of the physical principles that make the engine work are still operating. As the engine slows, the governor responds by opening the throttle plate wide. Fuel flow continues even though the ignition has been shut off. The result can be afterfire. To prevent this from happening, anti-afterfire solenoids have been developed. They work almost like an electrically controlled plug. When the ignition switch is in the on, run, or start position, battery current is applied to the solenoid. This causes a spring-loaded plunger to retract into the solenoid's body. When the engine ignition is turned to the off position, the current to the solenoid is cut, and the plunger returns to its relaxed, extended position. This forces the plunger into the emulsion tube and prevents any more fuel flow to the engine. With the fuel flow cut off immediately, there's little chance of afterfire. Throughout this video, we've discussed the theory behind all carburetors and some of the features you'll find on today's modern carburetors. With this knowledge, you'll be prepared to deal with older carburation systems, newer carburetors in use today, and the carburetors of the future. This knowledge is your foundation for troubleshooting carburetor problems. Now, it's time for you to put that knowledge to work for your customers. Okay. Troubleshooting carburation systems can be tricky, but there are some procedures you can follow which will make it easier to diagnose and repair carburetor problems correctly and efficiently the first time. You'll find those procedures outlined thoroughly in your 1996 Technical Update Seminar Notebook. In this video, we'll actually demonstrate the techniques described in the section headed Troubleshooting Carburation Systems. Before you conduct these procedures, you need to first test the ignition system with a spark tester and the engine compression components with a leak down tester. Let's assume that we've already tested the ignition and the compression. These appear to be okay. So, our next step is begin testing the carburation system. Most carburetor problems fall into one of three categories: starting problems, performance problems, and leakage. What's really confusing is when a carburetor seems to have problems in all three categories. The procedures we'll cover here can be used whether you're dealing with one problem or more. Now, let's start troubleshooting. When you're dealing with starting problems, there are several main issues you should check. First, Check the choke adjustment. This is a source of trouble more often than you might think. In some cases, a carburetor has been removed, cleaned, inspected, and reinstalled, and it works fine after that, even though the technician found nothing definitively wrong with it. What's probably happened is that the choke, left partially open before, is now adjusted properly. So, checking the choke early in your troubleshooting can be a big time saver. The second thing you'll want to do is make sure fuel is reaching the carburetor. Mechanically clamp off the fuel line to stop the fuel flow. Remove the line from the carburetor inlet fitting. Next, with a fuel cap installed, release the clamp and let the fuel run into an approved container. If the flow is as wide as the inside diameter of the line, you'll know that gasoline is being delivered to the inlet fitting. Some engine models use a primer bulb system to force fuel up to the main nozzle, similar to a choke system. How can you confirm that the problem is not in the primer? Remove the air cleaner assembly and look directly into the throat of the carburetor. You should see a pulse of fuel each time the primer bulb is depressed. Fortunately, there's an easy and accurate way to check fuel delivery to the combustion chamber once you've verified the choke position or primer operation. Turn to the humble spark plug. If you've tried to start the engine repeatedly with the choke on or the engine properly primed and the spark plug is dry, then you know that fuel is not being delivered from the carburetor to the combustion chamber. This could be caused by a blocked main jet, improper venting of the fuel tank or bowl, or even an air leak between the choke plate and the combustion chamber. If, on the other hand, the plug is extremely wet, the choke may be stuck closed, or the engine has been over-choked or over-primed. Sometimes carburetors with anti-after fire solenoids experience starting problems. This can happen if the solenoid is not receiving electric current, or it can also happen when dirty gas is used, or gas has been stored a long time and has gone stale. Test the anti-after fire solenoid system by checking for battery voltage at the spade connector with the key switch in the on or run position. A positive result indicates the problem lies somewhere else. Attach one pole of a 9-volt battery to the spade and the other post of the battery to the solenoid case or black ground lead, if there is one. If the plunger activates without sticking, the solenoid should be considered good. Finally, be sure to check the main jet of the carburetor for debris. This can cause the engine to appear to be underchoked and, in some cases, can completely stop fuel from flowing into the combustion chamber. As you've seen, a number of factors can cause starting problems. While choke operation is common, it's not the only answer. Performance is another category of carburation problems, and they come in many varieties. Maybe the engine won't idle, or idles poorly, or it may run poorly at top no-load speeds, or under load, or there may be a combination of these symptoms. The problem is most commonly described as hunting and surging. In most of these hunting and surging problems, the cause is a lack of fuel, not an overly rich fuel condition. And believe it or not, more than 95% of all carburetor performance problems are caused by dirt or debris in the system. However, before you can accurately diagnose a performance problem, you have to determine whether you have a governor problem or a carburetor problem. This is where your understanding of carburetor theory really comes into play. Separating a possible governor problem from a carburetor problem can be different in each complaint. To begin, you'll need to make sure the governor system is adjusted and operating properly. The next step is to make sure the idle mixture is properly adjusted. If the engine hunts and surges only at true idle, when the linkage is against the idle stop, as shown here, you know you don't have a governor problem. Why? Because at true idle, the governor has no effect on the engine's operation. If there's no problem at true idle, you'll want to check next for hunting and surging at governed idle speed. To separate the governor system from the carburetor at governed idle, hold the throttle plate linkage against the idle stop and increase the idle speed to the governed idle specification. If the engine runs well without any hunting or surging, return the engine speed to the proper setting. If the engine is brought up to the proper governed idle speed using the governed idle spring and hunting and surging returns, chances are good there's a governed idle spring or linkage problem. Keep in mind that if there's no appreciable load, the fuel is provided by the idle circuit or the transitional circuit or both. If the engine never did settle down to a smooth idle, you have a carburetor problem. Now, what if the engine hunts and surges at top no-load speed only? Again, you'll need to determine whether the problem lies with the governor system or the carburetor. Begin with the procedure we just described for testing governed idle, hunting, and surging. Once the engine is idling smoothly, hold the throttle plate linkage against the idle stop. Turn the idle speed screw until the engine is running at the proper top no-load speed. Make sure you hold the throttle plate linkage against the idle speed screw at all times. If the hunting and surging continues, you likely have a carburetor problem. If the hunting and surging disappears, you likely have a governor spring problem. Don't forget to readjust the idle speed screws to specifications. What if the engine hunts and surges only under a load? In this case, the problem is nearly always the carburetor. Why? Because when the carburetor delivers fuel under load, it feeds fuel almost exclusively through the main nozzle. Once the engine is loaded or doing work, the governor system has little additional effect on performance. Of course, there are times when problems don't fall into nice, neat categories. Sometimes an engine will exhibit multiple symptoms. Here again, your understanding of carburetor theory will play a large part in your success. For example, let's consider an engine which hunts and surges at idle and top no-load speed, but runs well under load. We can assume that the air bleeds, main jet, and the main fuel supply are all okay, since performance under load is acceptable. When we also consider that the reservoir of fuel feeding to the engine during idle and top no load is pulled through this common circuit, it becomes evident that the idle transitional circuit must be the source of our problem. What about the opposite problem? The engine only performs poorly under load. Under load performance problems are almost exclusively caused by debris in the main jet, nozzle, or air bleeds. To determine where the debris is most likely to be, check the engine's exhaust. Black smoke results from an excess of fuel, indicating that the air bleed may be blocked. No smoke and no black residue on the muffler deflector indicates a lack of fuel, and most commonly an obstructed main jet. Here's a troubleshooting tip for float-style carburetors that have pilot jets. Even seasoned veterans will appreciate this tip. A performance problem can result when the pilot jet fuel orifice is completely or partially blocked. This can be caused by debris and in some cases by fiber strands from non-original fuel filters. What are the symptoms? If the engine runs well at idle and top no load, but hesitates or stumbles at light load, the pilot jet orifice or a transitional hole may be partially blocked. If the engine will not idle at all, the orifice may be completely blocked. The solution, of course, is to remove the offending debris. Now, let's move on to our final problem category, carburetor leakage. It's one of the most annoying problems in the field. True factory defects are uncommon, and tests show that many of the carburetors returned to Briggs & Stratton over the years are structurally acceptable. So why do leakage problems persist? In a word, dirt. The overwhelming majority of carburetor leakage problems is caused by dirt or other foreign material. There is, however, a small percentage of carburetors whose components might be affected by corrosion, inappropriate fuels, or damage, and may cause leakage. So don't assume that the components are good or overlook any possible cause. Take extra care to prove the integrity of the carburetor and you'll increase your rate of first-time successful repairs. There are typically 3 situations in which leakage may occur: while the engine is not running, sometimes called a static leak, while the engine is running, and during or after coast down. Let's consider these individually. To tell where a static leak is occurring, begin by removing the carburetor from the engine and removing the float bowl. Make sure the float assembly contains no liquid, since retained liquid can affect the outcome of your tests. Wet the needle and seat area with a small amount of gasoline and use a thumb pump to pressurize the inlet needle to at least 8 psi. The inlet needle should pop off and reseal at 2 psi or greater. If it doesn't, clean or replace both needle and seat and test again. If the needle seals and holds pressure at 2 psi or greater for at least 5 minutes, consider it acceptable. Otherwise, you'll need to do some additional testing. Now, we'll test for porosity or external leakage. To do this, invert the carburetor and partially submerge it in water so that the needle and seat area, as well as the inlet fitting, are submerged. Hold the float with a finger to assure the seal. Note that after this test, you'll need to replace the part containing the rubber-like portion of the needle and seat. Now, pressurize the inlet needle to 8 psi. If bubbles erupt from the casting or the inlet needle and seat area, there is porosity in the carburetor. If the component parts did not show any bubbles, check the float by immersing it carefully in warm water. Watch for bubbles around the seam. Another method that has been used to successfully test for static leaks is done with a simple 2-quart freestanding tank. Fill the tank with gasoline and place it between 12 and 18 inches above the test bench. Measure this from the top of the fuel tank. Attach the fuel line to the carburetor you're testing and open the inline fuel shutoff. Place a piece of paper under the carburetor and let it stand in a catch basin or drain pan overnight. In the morning, you'll know whether static leakage is a problem or not. If all components test okay, it's safe to assume that the leakage problem was caused by dirt or debris. To correct these problems, it's very important to follow the next few steps carefully. Start with the fuel supply. Drain the fuel tank completely and inspect it for debris, dirt, or scaling. Depending on what you find, you may clean the tank or decide to replace it. Once the tank is okay, remove all fuel lines and filters and replace them with new parts which meet Briggs & Stratton specs. Disassemble the carburetor. Then, thoroughly remove and check every removable internal part. Sometimes dirt can be very hard to find. Take the inlet seat, for example. Dirt and debris can hide behind the seat, only to cause leakage in the future. If the seat is removable, do it now. Proper procedures for seat removal are described in your repair manual. Now, let's look at the last 2 categories: leakage while operating or during coast down. In either case, you'll use the same procedures. Most cases of leakage during operation or coast down are caused by the problems we just discussed: dirt and debris. There are, however, some additional situations which can cause either external or internal leakage. External leaks could be caused by loose or damaged inlet fittings, or tank strap assemblies, or external gaskets which are loose, torn, or missing altogether. If the engine displays a leak through the brass drain in the carburetor's throat, or if it wets the air cleaner element with fuel, you're dealing with internal leakage. Again, there are a number of possible causes. A loose or damaged main nozzle on the 2-piece flowjet model, using an auxiliary electronic fuel pump, a clogged air filter element on externally vented carburetors, a partially closed choke plate, a fuel supply which is either too large or which is more than 42 inches above the inlet fitting, excessive vibration, or an incorrectly sized fuel inlet seat. Now, let's take a quick look at troubleshooting a special type of carburetor, the two-piece flow jet. This carburetor's unique design can make it challenging to troubleshoot. It has a main nozzle which bisects the carburetor's body. Near the base or large end of the main nozzle tube is a chamfered area that provides a seal between the emulsion cavity and the carburetor's fuel bowl. If there is any defect, dirt, or corrosion on the surface of the sealing area, either the brass tube or the carburetor casting, a leakage problem could result that looks exactly like a damaged or dirty needle and seat. How can you correct this? First, take the old nozzle and remove the threads using a bench grinder. Place a small amount of lapping compound on the nozzle and insert it into the carburetor's body. Using a jet screwdriver, gently lap the nozzle, just as you would lap a valve. Remove the old nozzle and completely clean the carburetor body. Now you'll install a new nozzle with one addition. Install the Teflon washer from a 391-413 carb repair kit over the tube. And seat it on the sealing surface of the new nozzle. The washer acts like a gasket, providing a better sealing surface for both the nozzle and the carburetor's body. There is one last service tip I'd like to share, which can help you avoid causing your own leaks. You see, when a fuel filter is removed, a small amount of the inner rubber hose is rolled up as the barbed end of the filter is pulled out. This small amount of rubber can find its way into the carburetor, causing both obstruction and leaks. Because the debris is so small, it is very difficult to see with the naked eye. So, whenever you remove a fuel filter while repairing a leaky carburetor, replace it, but also replace the fuel line. And never use a bolt or threaded object to plug a fuel line during repair. The threads will cut the rubber hose and make the debris problem worse. By following the procedures we've demonstrated here, you'll save both time and money by increasing the number of repairs you complete successfully the first time. You'll also find it helpful to review your 1996 Technical Update Seminar notebook occasionally. You may find the troubleshooting summary particularly useful.